Good afternoon from Goddard Space Flight Center in Greenbelt, Maryland. Welcome to all who are joining us in person and those who are joining from our Goddard IBM stream. Thank you. You are joining the Goddard series called Engage. Today's topic is Moon to Mars. How's the weather out there? The Engage series was created as a vehicle to inform employees about what kinds of things are going on at where you're working. The center director at the time thought it was very important that the people who work here know about all the work going on here. Sometimes we get into our own projects and we lose sight of all the other things going on, and that's what the Engage series does. I can also tell you, we're going to learn about the Moon to Mars mission and how we study the sun's energy and how that impacts things from communications to radiation for our astronauts. And we're going to learn from some of the best people to tell us about that. So our moderator today is going to be Dr. Alex Young. He is the Associate Director for Science and Heliophysics Science Division. Actually, Dr. Jari Carlotto de Vega. She is the Director of Moon to Mars Space Weather Analysis Office, where she provides the real-time space weather conditions using state-of-the-art models. She came to Goddard as a grad student. And then there's Dr. Alexa Halford, a space physics researcher at Goddard who's working on the Artemis mission, as well as many others. She completed her PhD at the University of Newcastle in New South Wales, Australia. So I'm going to turn it over to Alex Young. Thank you.
Great. Thank you, Dina. So before I actually talk a little bit, I actually want each of you to just introduce yourself specifically. So why don't we start across?
Me first?
Go first.
Hi, my name is Dr. Jari Collado Vega, like Dina said. I'm from Puerto Rico. I've been at Goddard, if you count the summer internship, about 19 years. I started as an intern, then I did a pathway program in what is called Pathways. Back then it was called co-op program. And I was actually studying my master's in Puerto Rico by the time, so I have to move back and forth every 6 months, so it was kind of interesting. And then I moved here and did my PhD at Catholic University of America in Washington, D.C. in physics. And in 2013, that's when I got my position at Goddard, like permanent position. And that's when I actually started doing space weather. So it has been quite some time now. Okay.
Hi, my name's Alexa Halford. My pronouns are she, her. And I got into science at a really early age. When I was about 2 or 3, I saw a butterfly in the backyard, and I knew that butterflies had 2 wings, right? So I wanted to see it open up, and I stayed very still, especially for a toddler. And sure enough, as it opened its wings, I saw that it didn't have 2, it had 4. And I remember thinking, I have to see this again, right? So buzzing with excitement, I sat there trying to wait for it seemed like an eternity, to open up again. And sure enough, it had 4 wings, ran off, wasn't a scientist yet because I only got 2, observations, but ran off, probably scared the poor thing to death, and went running home to tell my mom, butterflies have 4 wings. And sure enough, a couple days later, got really lucky. Nova, because my mom didn't believe me, right? Because butterflies, 2 wings. Nova had a special on, and sure enough, they talked about butterflies having 4 wings. And that sense of discovery I didn't care that somebody else had discovered it, but that sense of discovery of knowing about what happened, and finding something out about the world around me myself led me to a career in physics, where I went to undergrad at Augsburg University in Minneapolis, Minnesota, small school. As my dad liked to say, that's what happens when you take up space at college. You become a space physicist. And I had that sense of discovery again when my professor gave me a bunch of pictures. They just looked like these colored plots, no idea what anything meant, and he told me to find something interesting. And I came back about a week or so later and said, well, here's this thing that happens every morning in the sky, and if you look at it, it happens in both hemispheres, and it's kind of the same in both hemispheres. And his response was, oh, that's the aurora. We already know all about it. Again, something that was discovered long, long ago before me, but I discovered it for the first time myself, and that led me on this path then to be a space physicist and really get into space weather. So I went and continued my education at University of Colorado Boulder, where I got my master's in astrophysics and planetary sciences, then went down to Newcastle, Australia to finish off working there on my PhD with Brian Fraser. Fantastic experience. I think I learned just as much science as I did just about culture and working with people by going overseas, and got to learn a lot of new slang, which is always fun. Then went off and did a postdoc at Dartmouth College with the Barrel mission, which was another incredibly cool experience where we got to launch balloons down in Antarctica. Unfortunately, I had to stay in the northern hemisphere where it was much colder, and help coordinate with the different satellite missions, specifically the Van Allen probes. But then we got to have some field work that I did get to join in Sweden, which was really fun, and that just solidified this is my field. Then came down to Goddard as a contractor, spent some time at the Aerospace Corporation for a bit, and then finally came back a couple of years as a civil servant here, where I'm now the Associate Director for the Ionospheric, Thermospheric, Mesospheric Lab, and the Strategic Lead for Heliophysics and Space Weather for Artemis at Goddard. So, sorry, that was a long
that's
journey.
great. A lot of good stuff
meandering
there.
Journey.
Thank you, Jari and Alexa. So I will introduce myself again. My name is Alex Young. My pronouns are he and his. I am also a heliophysicist, particular solar physics. I had kind of a long start also in terms of science. As a kid, I used to take everything apart in my parents' house, which drove them crazy because I wanted to see how everything worked. But I got excited really by science from two main things. The science in astronomy at the time, which was Voyager, Space Shuttle, and Cosmos, but then also watching, and I'm not old enough for the original Star Trek, but watching the syndication of the original Star Trek. So those are the things that got me into science, and was a good science nerd in high school and started a science club and did science fair and all that. Went to Florida State University in physics, studying high energy physics and quantum chaos. Then I went to the University of New Hampshire for a master's in high energy astrophysics and then a PhD in high energy solar physics. And first job out of the gates was here at Goddard as a contractor in 2000. And then in 2012, I became a civil servant and the associate director for science in the Heliophysics Science Division. And where my job really also focuses not just on the research, but knowing what all my colleagues are doing, trying my best to understand it, and help share that with not only people at Goddard across the agency, but the public at large. So science communication and bringing our science to as many people as possible. So I'm excited to be here to talk about the overlap between Artemis, our program for Moon to Mars, and space weather. So if you could put the first slide up, please. Okay, there we are. So kind of starts here. It's not all about the sun, but a lot of what we're dealing with starts with the sun. What comes off the sun creates a very dynamic environment when it interacts with planets. A lot of other things, exciting things are happening, depending on whether or not they have atmospheres, magnetospheres. It makes it a very exciting dynamic situation and system. And one of the areas that's important is what are the impacts on our ability to send people back to the moon and to beyond to Mars, communications, radiation, all of these aspects of the environment that are created. So that's what these two are going to focus on today, is that environment and their roles in this program. So I want to start with you, Alexa, and talk about what is your role in the Artemis program.
Yeah, so as the strategy lead here for the Artemis Gaggle, that's our, I think, official name, or that's at least the only name we refer to ourselves as. It's a group of people from across different directorates and different divisions. So we have a planetary counterpart, Kelsey Young, who helps lead a lot of the stuff with the planetary endeavors for Artemis. And we work with people in many different divisions, whether it's 450 with communications or 600 or sorry, I'm 600 or 700, 500, whatever. And a lot of what we try to do is to just identify what all the different opportunities are and make sure that we're all aware of them, because there's a lot of potential and great things we could do by working together. And sometimes we don't always do that well. So one of the examples is LunaNet. LunaNet is the conception for how we're going to have all of our communications with the astronauts when they're on the surface. And it will include search and rescue and stuff like that as well. Well, by understanding and knowing that this opportunity is going forward and working with 450, we're hoping that we could see that as an opportunity to also include space weather stuff on it as well, because that will be important for search and rescue and for the astronauts' health, and just understanding even from a basic standpoint of, if a LunaNet node goes out, why did it go out? Was it the space weather that caused that problem? So by having these kinds of discussions and connections, we can find these unique opportunities that can benefit both the science and Artemis itself. We're both trying to find ways to enable Artemis and be enabled by Artemis. And so that's a really kind of cool thing. And then with it too, we can look much further, because we do want to be a strategic group, and Artemis is running fast and it's sometimes hard to keep up with it. So some of the opportunities we've probably missed because we're just trying to get up to speed. But by looking longer term into the future, we can not only think about what's happening with Artemis on the moon, but also start preparing and thinking about where we're going when it comes to Mars. And Mars is going to be really interesting, because not only will we have to think about the space weather impacts coming and driven completely by the sun, and forgive me, but as the ITM Associate Lab Chief, I have to say this, space weather can also be driven by terrestrial weather or Martian weather. And so understanding those connections and how it will impact specifically communications and astronaut health, and just not just astronaut health, but also the health of the technologies that will keep the astronauts alive, is also really important. So that's kind of the fun thing I get to do with this.
So can you put up the last slide? So I just wanted you to speak real quickly to the last slide, and then I want to connect with how this relates to what Jari does.
Oh yeah, so this is one of our big ideas, big pictures of what we want to do going forward. So we know that some of our colleagues out at Johnson are working on different ways for astronauts to be able to visualize different information coming down to them, whether it's something like a Google Glass or if it's something like an iPad, which we've depicted here. And the reason why we want to look at these new ways of conveying information is that we can test them when the astronauts are on the moon and see if they'll be ready for when the astronauts are on Mars, when they're going to have that huge time delay between communication with Earth and them. So we want to make sure that we're building in all the different types of analysis tools they'll need to keep themselves safe. Specifically, is there something coming that you need to be worried about? Do you need to head back to a shelter and make sure that you're protecting yourselves from radiation? That's our big concern at the moment. And so having a tool like this, where we can display a lot of the different space weather tools that we use and that our forecasters use, whether they're at NOAA, SRAG, or here at Goddard, and then training astronauts how to use them and making sure that they're able to be displayed on something that's easily accessible so that they can see and get that actionable information in a very high risk, high kind of emotional state, and know what to do is really important. And so that's where we have this kind of concept of, could you have a tablet that would have all this information, maybe on the moon, have it be a demo where they could provide feedback and say, this was useful, this was not. This was something that was something that I could see using again in the future, and this was just too much data, and I need something that's faster and more concise. And you can see in the bottom right-hand corner is actually one of the kind of types of graphs that SRAG currently uses at their site, that the astronauts don't necessarily get that themselves, but this is trying to make that one step closer. And that's where, Jari, you guys are doing a lot of work with that.
Yeah, so Jari, do you want to elaborate first to talk about what is your overall role with Artemis, but then the connection here, and I know there's a lot of other things that you do for the agency and beyond.
So in terms of the Moon to Mars Space Analysis Office, my office actually was established in 2020, so during the pandemic, to support NASA SRAG into the human exploration activities. We know that SRAG is the one that supports the U.S. crew members aboard the ISS. They have a console that they operate. They look at the satellite imagery, and they also, look at the radiation environment. Because NASA plans to go beyond the LEO orbit, new capabilities are needed in terms of how we monitor the space radiation environment, the modeling of the space radiation environment, and also the communications, how we communicate to the crew about their health and safety. Because we want to go to deep space, right, beyond the Sun-Earth line, we need an organization that has that kind of capability. That's where the Moon to Mars comes in, which I'm going to call from now on M2M. That's how we call it. So M2M actually will be providing new capabilities in support to NASA's track by developing new tools that will actually help analyze the radiation environment. Not only that, we're actually going to be also, like we have been for many years now, supporting NASA robotic missions. And we're going to do also space weather assessments for launch activities. We do that too for NASA payloads. And we also do analysis for anomalies. In terms of Artemis, my team now, we do the support for NASA missions every day from 8 a.m. to 4 p.m. But for Artemis, we're going to be 24/7. If you want to develop new capabilities, new tools, you have to test them in the real-time environment. So we're going to be like the test bed and proving grounds of those capabilities. So we're getting very excited, but every time, something happens, we have to go back to the old schedule. So it has been kind of like a crazy month for us. But my team is amazing, and we're definitely ready to go. And not only that, we're also supporting NASA track all the time, like Alexa said. One thing I always point out, NOAA Space Weather Prediction Center, SWIFT, is and will be always the official organization for space weather forecasting to the nation. That's not going to change. Here, our team is going to work as a test bed, as a proving grounds of those capabilities that eventually will be transitioned to those operational agencies like NOAA.
Mm-hmm. So can you talk a little bit about what sort of things you do broader for the robotic missions, and then how does that connect with Artemis and human spaceflight?
In terms of the robotic missions, and this is a nice slide that shows one of the simulations that my team does, we work together with NASA Track, and there's also the Community Coordinated Modeling Center, CCMC. And the idea is for us to support NASA robotic missions. When my team sees an event, solar flare, a CME from the sun, it doesn't matter where it's going or where the source is, we analyze it. Because we're protecting NASA missions across the solar system. So we have to know where it's going. So don't get me wrong, right now we're kind of blind because we're only seeing the Earth face in this right now because of the way that SOHO and Stereo A are close together. Those are two missions that we use to analyze the coronal mass ejections. So in terms of how we support the NASA missions, this is an event that happened, I think it's a 2012 event. It was a big CME, like you can see there. We actually missed it. It went straight to stereo ahead, as you can see there. The middle circle is the sun, right? And you see the Earth on the right. You see Venus and Mars. So the idea for our team is like we analyze, we measure it, we run the simulation, and then we send notifications out to the robotic missions for them to know if there's something going their way. We don't make any decisions for them. They make the decisions, but our value is to keep them informed of what is happening. In terms of this event, this was a very interesting event because something like that could definitely happen at Earth. Every day the sun is really active and is sometimes unpredictable. Sometimes everything is quiet and people are like, my team gets scared, like, oh no, it's getting quiet. And then all of a sudden, boom, a solar flare with a high intensity happens. It has an associated CME, and then it has a solar energetic particles. These are the particles that are accelerated by those events that could be the problematic cause for the radiation environment for the astronauts. They cause problems to the instruments of satellites. And those are the particles that we're developing the models for at this point in terms of Artemis. In terms of the other missions, we send them notifications about everything that is heading their way so they know there's something going on.
Mm-hmm. So related to that, just curious, what do they do afterwards? Do they look to you for anything after the fact?
That's the anomaly part. Unfortunately, space weather can affect the instrumentation, and that's why we're here, right? So we can mitigate any of those effects. And sometimes they have anomalies. The missions have anomalies, and they send us requests Did space weather had anything to do with this? So we have to be ready to respond to those anomaly requests. And what happens is, after we send them the assessment, they actually sometimes meet in person, and then decisions, critical decisions are made because of those assessments. We have helped so many missions across the years at NASA, and not only the missions that are already up there, but also developing missions. Because remember, sometimes you build a mission during solar minimum, and then you're like, okay, nothing's gonna happen. And by the time you launch, it's solar maximum. What are you gonna do then? So they have to plan for a space weather event, and that's something that I always try to encourage the missions to do.
So one last question, and I'm going to ask Alexa a few things. So what sort of are the recent NASA payloads and launch activities that you've worked with?
We do a lot of collaborations. We're a NASA organization, so we do research development, right? So we don't want to get stuck here. So for us, the moon is amazing. It's the first goal that we're going to go, but then we have to look for Mars. So we have collaborations with Maven, Curiosity Rad. With Maven, for example, we're trying to develop a collaboration where we could actually validate the events that we predict towards Mars, so that we know that we're doing a good job with that. Not only that, how fast we communicate those events to the Maven team. We have collaborations with Solar Orbiter and Parker Solar Probe. Those collaborations are a little bit more interesting. You know, when we send notifications to the missions, it's everything that could impact the mission. But for Solar Orbiter and Parker Solar Probe, we send the notifications out for anything. We send the information to them for anything that is close by, because we want to make sure that they know where to look and when to look, because their missions built to actually analyze this, hazardous events, and that's the collaboration that we have with them.
Great, thank you. So Alexa, can you talk a little bit about the science, the heliophysics science associated with Artemis?
Yeah, there's so much cool science that we're going to gain from this. I mean, I think of the moon really as the new Antarctica. Back in the early 1900s, or maybe even late 1800s, when we first started going to Antarctica, throw a balloon up, see the geography. Okay, cool. Who would have ever thought that, 100 plus years on, almost every single science field would have benefited from that. And I think that's really what the moon is today. When we look at the moon, we know that we're going to be able to study the ancient sun. So as the sun keeps spewing out these different types of particles, it gets embedded into the regolith of the moon. And in fact, you can actually see how that has impacted where the remnant magnetic fields are on the moon. So as you see, the moon used to have a magnetic field when it had a molten core, and then that's now completely dead. But it's kind of like if you've had a bunch of paper clips on a magnet, and they come sort of magnetize themselves, but then it eventually fades away. The moon's magnetic field is sort of fading away, right? And so these magnetic fields, they push particles around, and it actually changes the albedo of the moon around it. So you can see where there's bright spots that are kind of protected from the magnetic field, and then darker spots that are where more of the solar particles have impacted. And so we can actually go and look at the different chemistry changes from that and see how our sun itself has changed over the millennia. So that's a huge thing. That's going to be something that will help us tie into not just how our star has necessarily changed, but then you look at other stars, other stellar kind of processes that are similar to the sun, and will really help us connect our sun to all these other data points that we can get, which is fantastic. Another thing that I think is really kind of interesting and cool, to me at least, is looking at how the solar wind interacts with that regolith and creates the exosphere of the moon. And that is going to be incredibly interesting then to compare to our own exosphere, to the Martian exosphere, because they're all three very different data points, but the physics should be somewhat similar. There's different physics processes added in, of course, but being able to see if we can model and understand them all will give us more confidence that we do understand the important physics involved, as well as just, being able to see how it might look at other exoplanets themselves, right? So again, tying back to what makes the Earth really unique in the fact that we actually have life here, which I think is really kind of cool. And then we also use the moon as a platform to look back at Earth. So we have a CLIPS mission, well, we don't, Heliophysics as a community has a CLIPS mission going to the moon that's called Lexi. It's PI'd out of Boston University, and we do have collaborators here at Goddard for it. But it's using the moon as a way to look back at the Earth and see the entire magnetopause. I think, are you involved with that one too?
No.
Oh, okay, I thought maybe you were. I know it's close to kind of IMAP and storm stuff, and you're involved with that. That's right. And so that's going to be really, really kind of cool to look at and see the potential for this as a location to do a lot of really neat and interesting work with. And of course, Hermes then. Hermes is the first instrument package going up for the Gateway. And it is going to be able to provide us in situ measurements about the space weather there. Now, the really interesting thing about Gateway is it's going to tell us not just about some fundamental science questions, but it's also getting at fundamental applied science stuff as well. So having your instruments on such a big structure is a difficulty in and of itself. You're not necessarily going to get all the clean, pristine data that you would on a purely science mission. But it's data that you want because it's kind of right at the location where all your instruments are and where the humans are. And so learning how to deal with this kind of, I don't want to call it dirty data because it's incredibly useful data, but maybe not
robust.
That's a good word. Not as robust data. It's going to be incredibly valuable, not just from the Artemis standpoint, because we would like to have similar kinds of instrument packages then going wherever the astronauts would go in the solar system or onto the lunar surface, but also how we can then use that and thinking more broadly to applying it towards commercial satellites where you might get an opportunity to have something on there, or onto other kind of locations and places within our geospace system. And that gets at a really interesting problem that we have. In space, turns out that there's a lot of space. It's really hard to get a lot of coverage of data. And one of the problems we need is to be able to see how all these dynamics change in this kind of field. But our data points are so sparse and scarce that it's hard to really answer them. So if we can start getting used to using this less robust data, but have more of it, then we can start applying new machine learning tactics, new big data tactics to it, and really start answering some of these questions. And so it is a starting point for us as a field to really embrace this new kind of data and really start applying it and learning about it and addressing many, many more science questions. And of course, my favorite science that's going to be done at the moon is the stuff that I can't even think of. I am certain that there are questions that will come up as we go there and go along that we can't even imagine today. And that 100 years from now, people are going to look back at us and think that all these different fundamental science that we thought of right now is about as equivalent to throwing the balloon up in Antarctica and just seeing the geography. And so I'm really, really excited to see what's going to happen in the next 10, 20, 50 years there.
So, Jari, Alexa mentioned commercial space flight. So have your primary focus is, of course, to support NASA and NASA's assets across the agency. But have you had any work with commercial ventures? And if so, what happened?
Interesting question. I don't know if everybody here remembers the SpaceX event that happened in February. They lost some of their satellites because of a geomagnetic storm. When headquarters contacted me, my team had done all the analysis for the events, and I sent them the assessment really fast. And that's something that I'm really proud of the team. We're really organized. We have a database. We put that there all the time. Everything that we do is there. It's not only there, but it's linkage to everything. If you have a solar flare that was associated with a coronal mass ejection, that coronal mass ejection was associated to a geomagnetic storm. Everything is linked there. So I had the information right away. So I sent the information really fast. We were part of the first few meetings for SpaceX. And the idea that they want to have is to make sure that they have all the models available out there that could help them make better decisions in the future. We also collaborate now really close with NOAA, and we also had meetings with NOAA and Blue Origin. So we're now kind of like helping that development phase of, look, this is the model that we have. Maybe we can run a few events that could actually help you analyze the data and see if it will be a good idea to launch or not to this altitude at this point in time. And make sure that that's available to everybody, not only NASA, but also commercial organizations.
Okay, thank you. So one thing you mentioned to me, and perhaps you already talked about it, but you didn't use the term, but ISEP program. Can you tell me a little bit about what that is?
So the ISEP program started in 2018. That's the Integrated Solar Energetic Particle Warning System. It's a mouthful. So we call it ISEP. It's a program that started in conjunction with CMC and SRAG. And the idea was to transition models that were in the research community that could be used operationally. However, CCMC is an amazing organization, but they're not operational. So they needed kind of like that organization between research and operations, and that's where M2M sits. We're right there in the middle of the research to operations side.
The bridge between the Valley of Death, across the Valley of Death.
We're hanging from a thread right there. And what the project did, CCMC created what we call an SCP scoreboard, which has an ensemble of different models that could be used in real time that predict either a proton flux peak intensity, a proton flux event onset, or a profile. And we're using that SCP scoreboard. Actually, SRAG is already using it for the ISS, and we're going to be using for Artemis. As those are the tools that we're developing and progressing to make sure that they're going to be ready for operations. So they're actually going to be nowcasting and forecasting events, SCP events that could actually be dangerous for the astronauts. We're not only developing the tool in terms that we're analyzing and doing the validation in real time, but we're also developing the communication ways on how this is going to work. So we have a channel now with SRAG, directly with SRAG, and we're going to use that channel now for Artemis. So right now, for example, we only talk to them once a day, but for Artemis, it's going to be 3 times a day. So it's going to be an interesting way to see how everything goes, and the validation is going to be totally different. Right now, we actually have validated events, but remember, we only do 8 a.m. to 4 p.m. So when an event happens overnight, it's already delayed, and that also delays the forecast of the model. That's not the type of validation that we want to do, and that's why it's so important for us to go 24/7 when Artemis launches.
So for the audience, and we've talked about some of the things that happen on the sun. So we talked about solar flares, coronal mass ejections, and these particle events. So SEP, solar energetic particles. So why are those so important? Because obviously they're all important to some degree, but why is that the SEP so important in this situation? What makes that special or even more dangerous than other types of solar activity?
So the solar energetic particles, like I said, are the particles that get accelerated by the solar flare, the CMEs, or a combination of both. And they're accelerated to fractions of the speed of light. They're very high energy. They're the ones that can penetrate the capsule, that can penetrate the suits, and they can cause the radiation effects that could be dangerous for the astronaut's health and human body. That's why we're making sure that we can forecast these events. They're also problematic to robotic missions, but in terms of Artemis, we're focusing on the human environment and human body.
And a lot of the other space weather impacts that we get from different types of charged particles are things that we typically try to engineer around before you even launch. And so the surface charging, the internal charging, and even to some extent the single upset events or single event upsets. I always get the acronyms wrong.
Single event.
Thank you.
Single event upsets.
I'm dyslexic, so don't ask me for accuracy with acronyms. But those are things that we can try to shield and know about, or make sure that our software is designed to kind of reset when things happen. The solar energetic particle events are much, much harder to engineer a fix for. And so being able to forecast those is really important, because that's our only way to make sure that we're able to protect, whether it's the satellite, the technology, or the astronauts, And I think that's one of the big reasons why that's a huge push at the moment. Most other space weather events, you can work around to some extent. Of course, we'd like to not have to work around them, But this is one that's much, much harder to find a workaround.
Yeah, and remember, right now we do have astronauts, but they're in the International Space Station. They're inside the Earth's shield, which is the magnetic field, right? When we're talking about going to deep space, there's a different story. You know, even energies that we didn't care when you were talking about the ISS astronauts, now you care because there's nothing shielding the astronauts but the capsule and the suits. So there's also plans on how SHRAG, we're gonna be mentioning, you know, analyzing the environment to SHRAG, supporting SHRAG, and they're gonna be the ones talking to the flight control team, and they're making the decisions, a go or no go on EVA activities, for example, or if they have to tell, you know, go to shelter. You know, they're the ones making those decisions, so that's why our analysis is so important.
So I know you mentioned it, but just for the audience, remind us what SHRAG means.
Space Radiation Analysis Group is a Johnson Space Center group that supports the U.S. astronauts.
Great, thank you. So, Alexa, you talked about the not as well known impact of space weather that comes from terrestrial weather.
Yes.
Okay. So, I'd like if you could talk a little bit about that, and you know what's important about it, and what do we know so far.
Oh yeah, they're fantastic. There's gravity waves that can be set up by either mountains or just hurricanes and big terrestrial weather fronts that literally create waves in the atmosphere that then propagate up into the mesosphere and thermosphere and sometimes even higher that can in fact impact the ionosphere. And there's bubbles and blobs and all these fun things. And one of the big things that's often a concern with a lot of these is scintillation. And scintillation is something that can really impact our ability to have strong communication. And so that's one of the things that is really important. So of course, scintillation can also be impacted from flares heating the atmosphere as well. But this is one of those areas that we don't talk much about at all because there is so much energy coming from the sun that it sometimes gets forgotten. But it's really important because when you're having that communication coming down through, you know, from a satellite down to the Earth, you want to make sure you understand, you know, why it may be missed or why you didn't get it or why it's not doing as well. Other times, you know, you're thinking about communication on the ground, and this would be true potentially for Mars. You have, you know, over the horizon kind of communication where it's bouncing literally off the ionosphere. So if the ionosphere is moving around or the atmosphere is moving up and down, you might miss where you're trying to go. Now you can often engineer around it. You can say, well, let's move to a different frequency because it will then get to where you want to go and things like that. But it's still important to know. I think one of the big examples of this was during the 2017 September event, where Mexico unfortunately had the brunt of it, where there was a hurricane, an earthquake, and a solar storm, a big solar flare all at once. And this was important because the communication paths became really critical. You want to make sure you can communicate over long distances to make sure you can get help, especially if it was Puerto Rico or some of the other islands out there. But when you can't rely on that, you have to either go to other frequency ranges, which sometimes work, sometimes don't, or you have to go to line of sight communication. And so it's not so much that that space weather event was going to be incredibly harmful, it was just going to impede our ability to respond easily. And you wanted to make sure then that everyone knew exactly how they were going to be able to respond and what tool to use to communicate with others. And so that's where it becomes really important. And those lessons that we've learned here on Earth on how to deal with those space weather types of events, we can then apply when we go to either the moon, well, not so much the moon because it doesn't have much of an atmosphere, but Mars or other places too. And so that's where learning about these different types of physics and the engineering kind of practices for how to get around them is really valuable, and especially understanding why they will or won't work in different locations and why there might be some better engineering solutions as you go to these other locations in the solar system.
Yeah, and you know, talking about that storm in September, we transitioned out of the CCMC. We had an experimental group there, And that's where I started doing space weather analysis and things like that and research. And we actually got called from the disaster group here at Goddard because, it was Irma hurricane, Maria hurricane, and the ground radar in Puerto Rico was off.
Yep.
So they could not afford to have also all the satellites on space to also be down because they're gonna have a problem with that. The disaster group will not be able to actually monitor the activity that was going on the ground. So now we also participate of that group here at Goddard because even though that is a solar event, it can affect the communications on Earth that are super important for this kind of activities.
Yep.
Great. I know we're going to get to questions shortly, but I wanted to ask Alexa about something that I know that's exciting for you, and I've heard you talk about this in other contexts, but can you talk some about sonification of lunar data?
Sonification is so cool. And I don't know if it's true, but I'm going to make the bold claim that perhaps heliophysics used it first. I'm pretty certain that's actually not true, but I'm going to claim it anyway. Back in World War I, when we first started using radios, they would use the radios to actually detect bombs falling through the atmosphere. And you'd hear this, I can't whistle, but you'd hear that like descending tone. Yeah. And so, yeah, you'd hear that coming down. And what was happening was that they'd hear these tones and then nothing would happen. And it turns out that was VLF waves coming in from space. It was specifically what we then went on to call chorus waves, which chorus get their name because they happen to occur in the dawn area around the Earth, and they sound like a chorus of birds. Now we also then have hiss waves that are a little bit more earthward than the chorus waves, and they sound like a hissing cat or, angry birds, I guess, maybe. And so what would happen is back in the day when it was really hard, we didn't have supercomputers yet, so processing data was always difficult. An easy way to be able to analyze your data was actually to listen to it and listen for these different types of sounds, whether it was chorus waves, whether it was chirping, whether it was saucer events, whether it was these like little giraffes and things like this. And you can use it to actually identify things in your data. Now we've gone well past that. So like Mars has a new actual audio recorder there where they can listen to the wind on Mars, which is really neat. But on the moon, we have this really cool one that sits there, and it's a particle detector. And what they've done, it's the Crater event, or Crater mission, and they've actually taken the different energies and the different particle types and used that to give it a specific note and tone. And you can hear this wonderful kind of orchestral music almost of this stuff coming from deep, deep, deep space, like other galaxies coming and hitting the lunar surface and imparting their energy into that regolith, which is really kind of cool. And it's a really fun way to kind of get involved with your science. I know they've done this in astrophysics as well. Mm-hmm. And it's just really fun to use that sonification. And like I said, it has had historically an actual data analysis tool, been used as that kind of data analysis tool. And in fact, we still use a lot of the same kinds of techniques that are used to make sure that our mics don't sound tinny or don't have that. We use those same analysis techniques in our own data when analyzing those waves. And so there's a nice synergy between music and science here.
Great, thank you. So Dina, do I turn it over to you?
And you can find, if you search like NASA sounds or spooky sounds, they often do that at Halloween. There's some really fun ones.
That sounds great. The Office of Communications at Goddard has done a lot of programming with the National Philharmonic.
Yep.
I can't wait to tell them about that.
Yeah.
It sounds really cool.
Right.
Yeah.
Right. So thank you very much. Let's get to a few questions. Ooh. Okay, our first one is coming online, but if anyone in today's audience would like to ask a question, please use one of the microphones on either side of the audience. Okay, and of course, as soon as I go, here we go. We're up and running now. Okay, Fred online has asked, can you speak more about the interactions between Earth and space weather? What technical challenges have you overcome to make these connections? And as we collect more data, how do you see your approaches evolving?
Ooh, do you mind if I
go ahead.
take that one? So it's really kind of cool. Our first experience of really understanding the impact of space weather on technology was during the Carrington event, where we got to see a flare from the sun. In fact, the flare lasted so long that Carrington ran and called a friend who confirmed the observation and ran back, and he was still seeing it kind of dim out. So it was a long-lasting flare. We then saw, it was less than a day, I believe, later.
16 hours.
Yeah. Hit the Earth, and you saw the impact on the transformers, not the transformers,
Telegraph.
the telegraph system,
Telegraph.
another T word there, and telegraph system. And in fact, at times it was like causing fires, and they had to unplug them from the power grids, and you had all this extra energy. Don't count on space weather becoming the next new reliable energy anytime soon. It's way too episodic. But it was really kind of interesting, and it was, I think, the first real time we saw a huge impact on technology. Now, one of the things that's really cool is that we've seen this happen time and time again throughout history, whether it was in 1970s, there was also a time when it exploded an underwater mine, which was really kind of interesting. Of course, the 1989 blackout that took out most of the power in Canada and New England. There was a similar kind of event in I think it was the late 90s, early 2000s in South Africa. And so one of the things we're starting to see is this recognition that space weather can have real impacts. It's not just the radiation, it's induced currents in long power grids and pipelines and lots of other issues with GPS timing and stuff like that. Now we're continuing to make progress towards being able to forecast different environmental places and environmental data. But one of the big things that we're lacking is actual impact data. And that's really hard to get because companies don't necessarily like to say when something went wrong, right? And the other issue is that it doesn't always go wrong for all the systems. So like Galaxy 15 is a satellite that has historically had lots and lots of problems. In fact, when I was in high school, I was doing a satellite communication class I was taking Latin, but we didn't have a Latin teacher. So while I was in Wisconsin, the teacher was down in South Carolina. And Galaxy 15 used to be the satellite that, I think it was 15 still then, that had all of the beepers for doctors to use for getting messages about emergencies. And it got hit by, I think it was just a substorm. I'm not even sure it was a large storm. It was a small storm.
There was an event in August.
Oh, there was another one. So it took it out, and they actually took over our educational satellite. So we got a week or two off of school, which was kind of nice. But they then, had to switch there. Now, Galaxy 15 has had recently another one, but it has consistently had issues from time to time. The other Galaxy satellites, not so much. So what's wrong with that one? Is it just that it's so unlucky that it happens to always be in the path of these really narrow kind of tornado-like sort of events? Who knows?
Is it an error?
Is it an error? Yeah. And so that's one of the problems, is that if we don't get enough data about the actual impact, it's really hard to make that direct connection of it was this type of weather affecting this type of technology. And so that's been one of the big issues. Now we're currently continually, for many years, been trying to find ways of collecting that data. But I think there's been a lot of new initiatives, whether it's from some of the stuff that's come down from the Office of the President to work on space weather, and companies themselves starting to recognize that this might be actually really beneficial to them to learn about that and to collaborate with us. And so I think we're going to make progress in the next 10 to 20 years, but it's been an interesting journey for sure.
Yeah, and talking about the Carrington event, we saw auroras in Cuba and Puerto Rico. That's close to the equator. That has never happened after that. But, our team, the Heliophysics Science Division here, we have a lot of people doing research on this kind of interaction, and we actually have models now that try to recreate what would happen to the magnetic field of the Earth if an event like that actually hits. And, it will be really interesting and kind of catastrophic, but that's why we're here, right? Because that's why we're trying to analyze the event, try to do nowcast and forecast of these events, so we can mitigate anything that could happen to the satellites.
It's when you start realizing you have just a little bit of a mad scientist in you.
Yeah.
Just a little bit. No one's going to get really hurt. So just a little bit.
And talking about anomalies, we work with anomalies all the time. And I had people call me to my office and be like, can you help us see if space weather had anything to do with this. And I'm like, okay, yeah, what is the orbit? Well, it was around this area. And I'm like, okay, if you don't give me the exact details, there's no way I can help you. So that's just to give you an idea of how some organizations and some, even NASA internally, are so secretive about the problems, because there's a lot of things involved in that kind of situation.
Yep. You mentioned mitigate. We can mitigate issues. What would a mitigation be?
So a lot of times there's different types of mitigation we can do. So with power grids in particular, there's easy mitigations for things like the carry tuning event. And we've already put them in place more recently for brownouts, when we have just too much power on the power grid itself. You can take it off, you can offload it, you can, right now our power grid is very much interconnected, and you can kind of put stop places in there. And we've had large storms like the 1989 one again, and I think it's a real show of the safety precautions we've put in place that we haven't seen the same catastrophe again. And so as we experience these, we can put those things, put those little safety measures in place and learn how to safely ride through them, right? And another thing, like with pipelines, you can't necessarily turn a pipeline off, right? But you can go and check it more frequently to make sure that it doesn't have extra corrosion happening when there's been an increase in space weather. Satellites, you can have them power off for a bit.
That would be the last choice, though.
That would be the last choice. But there are things that you can do along the way if you need to. Often what happens is,
maneuver.
They'll maneuver, or you just let the single event upset happen and you just have it restart. Reset.
That's great.
Yeah.
This gentleman had a question.
Yeah, he was waiting for a while.
But what do we need to learn in order to better predict solar flares?
Oh,
if we could get data from inside the sun, that would be great.
So,
but you're not going to get that.
Yeah, that's a great question. That's actually well, Jari knows a lot about it. That's actually also my area of research.
Yeah.
It's really, really hard.
It's really hard.
The problem is, it's okay if I? Yeah. So the problem is, what's happening with the magnetic field, what's happening in the photosphere, which is the visible part where we can measure the magnetic field there, and what's happening in the corona is very difficult to understand, because the magnetic field down in the photosphere is very disordered and crazy, but it's very structured in the corona. But the action's happening in the corona, and we can't measure the magnetic field in the corona. I mean, we've only recently done it during an eclipse, maybe with DKIS, but the lines you need, the spectral lines you need are IR lines, are really hard to measure. So the direct measurement is really difficult. So that's one challenge.
Yeah.
But the other one is, a lot of what is happening with the generation of these magnetic fields is happening under the visible surface. And we have limited capabilities with something called helioseismology to start to understand these flows of plasma and how they generate magnetic fields. But overall, the physics of what governs those different scales and connections, we don't fully understand. And then the challenge with that is similar to the challenge with earth science, is you have several scales. You have the micro scales and the macro scales, and there's no computer in the world that can connect all those and couple those scales. And so the challenge of really predicting weather is very similar, certainly with computational models, to the sun. There's certain aspects that are more complicated here and vice versa at the sun, because they're the differences in physics. But as Jari was saying, right now our forecasting of flares is not so much different than how we do it with precipitation. It's a statistical measure of, we've seen this kind of sunspot 100 times, and so many times we got this kind of flare. So you can give yourself a percentage, just like precipitation, but it's not a real prediction. So, and if I missed anything, please add to that.
I will talk more about the improvements. What do we need, right? Right now, unfortunately, we're in an era that we're kind of blind, and I mentioned this at one point. There's only views of the sun on the Earth facing this. So you're actually missing half of the sun.
Yeah.
So on my team, like when we have an eruption on the backside, sometimes we just have to guess where the eruption is, like the source. Yeah. And that actually affects the simulation that will predict the impact on where it's going.
Does stereo help there?
So stereo was amazing, but stereo ahead is now close to Earth. It's like 20 degrees right now. So we're looking at the same face of the sun all the time.
Yep.
So
need
talking about that, we
need
have
an L3.
magnetograms that actually are looking. Those are the ones that we use to create like the magnetic field models that actually input into the simulation like this one.
Yeah.
We're only seeing now also the Earth facing this. So we can estimate the backside of the sun, but that doesn't mean that the sun is very unpredictable sometimes. It has eruptions that actually change the topology of the magnetic field locally that will affect how the model is predicting the magnetic field of the sun. So we need more observations.
Yep. So ESA is planning an L4. So it will.
L5.
Oh, sorry, L5. And then there's been calls for the US to also do an L4. And ideally, we did want to have an L3 as well. One way to get around having to have them at all the Lagrange points around the Earth is that some people have also suggested we do L1 monitors around as many planets as we can. So that even though they're not always going to be in quite the right configuration, on average, you'll have something that's looking at the sun from most angles.
Yeah. For Mars, for example, one of the ideas is to have an L1 Sun-Mars spacecraft there monitoring the solar wind affecting the planet. Because that's the only way that you could actually assert that you're going to have the analysis for the space weather environment at that planet.
And in the next coming months, we hope to have an MDL study for that Mars L1 mission. So hopefully, first step.
Parker Solar Probe now, to be completely honest, is going really close to sun. We have never done that either, right? So we're getting data also that we have never seen before because before it was all remote. So it was all far away. Now we're having data that we haven't received before, and now it's going to do conjunction campaigns, I was looking for that word, with Solar Orbiter.
Right.
Yeah.
And the idea is to actually use those two missions to understand better that magnetic field of the sun and what happens, like Alex says, in the corona.
Yep.
Yeah. So the solar orbiter is one of the things it's going to do. This is a global scale, but we can't see the poles, the magnetic field in the poles, and those are critical measurements. So solar orbiter is going to be moving out of the plane of the solar system about 24 degrees, and we'll see the poles and measure the magnetic field. So that's one thing that will help, probably more for dynamos and things like that, the global models. But even Solar Orbiter is now seeing flares and gave estimates about them on the other side. So we had an active region a couple weeks ago that was starting to do a lot of stuff as it was rotating out of view, but then Solar Orbiter was on the other side and actually measured it with an X-ray instrument and was able to make some connections with the kind of measurements we make over here. And so that's a first of its kind.
Yeah.
And all of that together is going to help.
And we had a far-sighted event, by the way, that's one of the ones that Alex is talking, that Solar Orbiter measured that created a very low inclination of the proton fluxes at Earth. Yeah. So it doesn't matter. Yes. We believe it's a dispersion of the particles from that event. It was so big and the shock was so high speed that it actually accelerated particles that could cause problems across the whole solar system. Yeah. So space weather is amazing. Is a nearly, is one of those fields that kind of new compared to astrophysics. Yeah. And there's so much more that we need to know about it too.
Yep.
Thank you very much.
Yeah. I think you.
This gentleman had a question.
Yes.
Yeah, I'm trying to phrase my question. So I work on C-cores, C-core 1, C-core 2, which are all C-core 2 is going to be an L1, C-core 1 is Earth orbiting, so they're all, again, in line.
Yeah. So Swifto and Ghost.
Yeah. Swifto goes you, yeah. And you mentioned that you've got like an MDL study coming up on doing a Mars L1 something. So kind of as NASA and NOAA are building out the punch and the C-cores, do you plan on using that data differently? I mean, or is it just kind of, are you going, like, how do you plan on feeding that and improving your models in a way compared to stereo A, stereo B, SOHO data?
So the interesting thing about the Swifto and the Ghost chronographs, they're going to be operational chronographs. We don't have that now.
Yep.
We have to wait for the data to get downloaded to the DSN, for example, network, and then from there to come and actually then we can see the CME. That delays the whole process,
Yep.
right? In terms of hours. So having an operational chronograph, that's going to make a huge difference in the way that we analyze this event. And also, we have models that depend on those measurements.
Yep.
So the faster we analyze the CME, the faster we can get a forecast for the energetic particles. So it's going to be a game changer.
Yeah, because I know Secore, it also has some onboard processing, so that if it's taking images and it sees something interesting, it'll up the rate
Yes.
of image taking, so it'll be like, oh, interesting.
Exactly.
Get you a much better.
Oh, believe me, we're waiting for it.
Yeah. We're
So-
working on it.
So from an operational standpoint, yeah, it's going to be a game changer. From a science standpoint, I think it's going to be one of those things that is used very much in the same way, but it's one more point of data that helps really build out your understanding. Now, specifically with like the L1 locations, not necessarily with Secore, but with like the particles, even we have currently out there ACE, Discover, SOHO, but I'm thinking more ACE and Discover because they have more particle stuff on them. Wind sometimes is out in that location. Sometimes Themis is out in front of the magnetosphere. Geotail as well. And one of the really interesting things we see with the in situ particles there instead of the remote sensing stuff, although I'm sure you could do some really cool stuff with the triangulation of remote sensing, but is that even though they're all circling L1, so all relatively in the same spot, they're not in the same spot and they don't always see the same things, and sometimes it can be very different what they see. And specifically L1 to Earth is 1 million miles or so, and what you see at ACE and Discover and then at Geotail or Themis when it's kind of outside the magnetosphere can be very different, because those magnetic fields coming from the sun might not really connect to the Earth. And so right now what we're getting from L1 is very much kind of, you have to think of it more as like a broad kind of climatological sort of pressure or pressure system maybe kind of thing, instead of so it might be raining in your town, it might be raining in the DMV area, but it's not raining in Greenbelt, but it's downpouring in Annapolis kind of thing. And so you might want to know that it's downpouring in Annapolis if you're having to drive home, but or I have to drive home. But you maybe, are more excited that it's not raining here at oh my goodness, where are we? Greenbelt. I was going to call it Greenberry. It's like, that's not right. And so you can go out for beers, with, before you head home or something like that. And so having all those data points, because we are so scarce with our data set, any new data is going to give us better insights, whether it's for forecasting or whether it's for us to actually understand the scale size and the dynamics that are happening within this whole system.
No, and it's going to increase all the models. It's going to improve the model. Any data, new data that we can get to the models, it's going to definitely improve them.
Yeah, we're so data starved. We will take any crumb we can get.
Right now,
Literally.
our training, when I train people to do the analysis for space weather in real time, most of the time we actually have to put stuff there that they actually have to do an educated guess of where it's going, because there's no other way around it. There's no images. Sometimes we don't get the data. Data gaps is a different story, because we get data gaps sometimes when it's not a good.
We're trying to predict when the weather's bad, and when the weather's bad, it's bad not just for other technologies and other satellites, it's also bad for the technologies that are trying to tell you that the weather's bad.
We had a solar flare not so long ago, and Ghost went into eclipse, and you could see the flare happen, and then boom, and you're like, no! So we have to use other, like they have the west and east, that we have to use the secondary to actually kind of like approximate what actually was the classification of that flare.
And so, but you've mentioned a lot about how, in a lot of ways, how much better the in situ data is. For instance, on Park Solar Probe, you're getting much closer in situ data than we've ever had before.
Yeah.
Just think if we had 20 of them.
Yeah, that was well, yeah. And this question is like, are there plans to figure out, other in situ data
Oh,
points
we
that
are.
closer in?
We just had the decadal survey.
Yeah.
And the community just submitted white papers for the decadal. And there's a lot there on new missions, new capabilities that could help us understand the environment better.
We need like a massive increase in budget. That would really help.
Always.
Yeah.
And the in situ data is usually magnetometer data, or
So-
what's the in situ data that you guys really?
So magnetometer data, particle data,
Yeah.
electric field data, if we can get it, that's
Just
sometimes
imagers.
not always there. Imagers, but that's more remote sensing, right? That's that's really what our bread and butter is for looking at what's happening right there. The particle data ideally would have electrons, protons, and then also include like helium, oxygen. Maybe depending on where you are, if you're in the magnetosphere, you might also want to include nitrogen or some other, maybe some molecules. But if you're in the ionosphere, you definitely want neutrals then as well. Those really help. Now, and if you can even get how much a particle has been ionized, that will tell you a lot more as well. So, whether it's a dosimeter that just kind of says, here's radiation that's hit, or it's something that's like this massive suite that gives you pitch angle information, energy spectral information that's like almost a continuum, and species information. We'll take whatever we can get. Of course, as a scientist, you want the whole shebang. As doing space weather and wanting something that's more real time and needs less processing to actually get to, a dosimeter and something kind of more simple is sometimes even better, because you can get that data faster and it doesn't need all the processing to then be incorporated into a model.
Yeah.
And so depending on what the use is really what drives what you need and want.
Not only that, for anomalies, like sometimes I get requests for anomalies and they're like, okay, can you tell us if space weather had anything to do with this? And we can give them an idea. But if you don't have in situ particle measurements, there's no way for me to tell
Yep.
if something actually happened on the spacecraft.
Yeah.
Right?
So this might be a good opportunity for me to ask that we are still actually recording.
Oh, okay.
And somebody online asked a question about the CUSP, the CubeSat for the study
Yeah.
of solar particles on
Yeah.
Artemis 1.
Yeah.
Familiar with that?
Yes.
Yeah,
Does
I
that
like that.
fit into getting more data for you?
It will be getting more data for us, and it would be amazing, right? And this is one of those opportunities that is why we have the Artemis gaggle and want to talk amongst everyone, is to find opportunities like this, like these ride shares and ride-alongs. So CUSP is actually going to go with Artemis 1, and then I don't think the plan has changed. I guess I haven't looked since the last launch thing, but it will be dropped off last, so that it can start flying out towards L1 and towards the inner heliosphere, and be able to get a bunch of that kind of information. And it's a great test case for many things. Not only is it going to give us new data, which is always fantastic, but then it's also going to give us, an opportunity to see how well we can do with these small CubeSats in these large missions going to other exotic locations. Most of our CubeSats have stayed right around Earth. And that is, as Darius stated, a very different environment than when you go into deep space.
Yeah.
And often the CubeSats and like the little helicopter too are sometimes you can be more risky with them, and so you don't necessarily have the rad hard equipment built in, and so it might be more susceptible, or is potentially more susceptible to some of these space weather effects. And so seeing this go and get some amazing data, and then also show, hopefully successfully, that you can have these kind of smaller missions going to these different locations is going to be, it's going to be phenomenal. I mean, it's just going to be really cool, and hopefully one of the first of a long line of partnerships with Heo and Helio to be able to get more data and to see more of space.
I love that idea. Thank you again for sticking around and asking
Yeah.
more questions and for the recording to continue.
Yes.
Thanks to Alex, Alexa, Jari. Thank you. Also want to thank those behind the scenes. We have Dustin, Travis, Bree, and Daryl. Thank you very much. Remind everyone that the Goddard Visitor Center in Greenbelt, Maryland has a beautiful solarium with sonification of the Solar Dynamics Observatory data, which is, you've got to see it. So please stop in the Goddard Visitor Center for that. Mark your calendars for the Artemis 1 launch we just mentioned. Next attempt is going to be on September 27th.
Yep.
Thank you.
Thank you so much. Thank you for
Thank
coming.
you. Yeah.